the integral test, corollary of theorem 6, the series sum of a sub n and from 1 to infinite of non-negative terms converges if and only if its partial sums are bounded from above. Here on this part we have graph for f of x equal to 1 over x squared. And here we have these rectangles under this graph. So the sum of the areas of these rectangles under the graph of f of x equal to 1 over x squared, that is less than the area under the graph. So what we have here on this part, s sub n is equal to, based on what our function is, 1 over x squared. Starting from this point, adding all these that we have for rectangles, sum of areas of these rectangles, we have 1 over 1 square plus 1 over 2 square, 1 over 3 square, 1 over 4 square, plus 3 dots plus 1 over n square. So that is equal to what we have on this part, that is equal to f of 1. So what we did was that x equal to 1, f of 1 equal to 1 over 1 square. So x equal to 1, then x equal to 2, so we have f of 2, then we have f of 3, f of n. Adding all these, that is less than f of 1 plus integral 1 over x squared dx, and this is from 1 to n. So that is less than f of 1 is equal to 1, so because we have 1 over 1 squared, that is 1 plus integral 1 over x squared times dx. This is from 1 to infinite. And that is less than 1 plus the answer for this part, integral, that is equal to 1. So adding these two numbers, 1 plus 1, it's equal to 2. So what we did, s of n is less than 2, or some of these rectangles, some of the areas of these rectangles, that is less than 2. Theorem 9, the integral test. Let a sub n be a sequence of positive terms. Suppose that a sub n is equal to f of n, where f is continuous, positive, decreasing function of x for all x greater than or equal to n is positive integer. Then the series sum of a sub n and from uppercase n to positive infinite, and the integral of f of x dx, this is from n to infinite, both converge or both diverge. Here on the side, based on this function y equal to f of x, and the conditions that we have for integral test, the series sum of a sub n and from 1 to infinite, and integral f of x dx from 1 to infinite, both converge or both diverge. Again, the conditions that we have for integral test is f for our function is continuous, positive, decreasing. So we have same thing on this part. Our function is continuous, positive, decreasing, and here on right side we have remainder terms. At this point we had n plus 1, continuous. On this part we have n plus 1. So these are called remainder terms. That is same here for part B. Here ending point was n, and here continuous we have n. So these are a sub n plus 1 starting from that point. Here we have remainder terms. So the remainder when using n terms is here in part A larger than the integral of f over n plus 1 to positive infinite, and the remainder when using n terms is smaller then the integral of f over n to infinite. So here part A larger than the integral, because these rectangles are above our graph, but this one, part B, is smaller because these rectangles are under our graph. Once for the remainder in the integral test, suppose a sub k is a sequence of positive terms with a sub k equal to f of k. F is continuous positive decreasing function of x for all x greater than or equal to n, and that sum of a sub n converges to uppercase S, then the remainder r sub n is equal to s minus s sub n, satisfy the inequalities integral f of x dx. This is from n plus 1 to infinite, that is less than or equal to r sub n, and that is less than or equal to integral f of x dx. That is from n to infinite. So what we had here on this part, these are conditions of integral test. And so we have continuous positive decreasing function. And this s sub n is for partial sums. Example, use the integral test to determine if the series shown below converges or diverges. Be sure to check the conditions of integral test are satisfied. What is given here on the spot, sum of 8 over 7 times k plus 12k is from 12 to infinite. So based on what we have for an integral test, let a sub n be a sequence of positive terms. Suppose that a sub n equal to f of n, where f is continuous positive decreasing function of x for all x greater than or equal to n, and n is positive integer. Then the series sum of a sub n from uppercase n to infinite, and the integral of f of x dx from uppercase n to infinite both converge or both diverge. So this is what we had for integral test. So we have to see whether the integral test can be applied to this series. So first identify f of n, which is equal to 8 over 7 times n plus 12. Since f of x is a rational function, whose only zero is negative 12 over 7. So what we have here in the denominator, f of n plus 12, that's equal to 0. So f of n equal to negative 12, n is negative 12 over 7. And this number is less than 12, so what we had for uppercase n, that is 12. This is what we had for uppercase n, 12. So this number is less than 12, and what that means, our function is continuous for all x greater than or equal to 12. Since both the numerator and denominator of x are always positive for all x greater than or equal to 12, so our f of x is positive. So here what we have for numerator is 8, and denominator we have 7x plus 12, because here I used f of x, so denominator 7x plus 12, and that is positive for all x greater than or equal to 12. Since the denominator of f of x, which is 7x plus 12, is always increasing, and the numerator is constant, so denominator increasing because that is for all x greater than or equal to 12, and the numerator is 8, and that is constant, so our function f of x is always decreasing. So what we had here on this part, continuous, positive, and here decreasing. What that means, our function f of x is continuous, positive, decreasing for all x greater than or equal to 12. So the conditions of the integral test are satisfied with n equal to 12. Now determine whether the integral f of x dx is equal to integral 8 over 7x plus 12 dx converges or diverges. So evaluate this integral 8 over 7x plus 12 dx. So integral 8 divided by 7x plus 12 times dx, that is equal to 8 over 7 natural log of absolute value of 7x plus 12 plus constant. So C for constant. Then after that step, apply the fundamental theorem of calculus to evaluate the integral. The integral of 8 over 7x plus 12 dx, and this is from 12 to infinite, that is equal to limit of what we had here on this part, limit of 8 over 7 natural log of absolute value of 7x plus 12. This is from 12 to b as b approaches infinite. Now substitute here, this is equal to limit of 8 over 7 natural log of absolute value of 7b plus 12 as b approaches infinite. So I use this part first, and then subtract what we had here. Instead of b, use 12. So we have 8 over 7 natural log. Here 12 times 7, then plus 12, that is equal to 96. So this part is equal to infinite. So since limit of 8 over 7 natural log of absolute value of 7b plus 12 as b approaches infinite is equal to infinite, the integral of 8 over 7x plus 12 dx from 12 to infinite diverges. So this one equal to infinite, that means our integral diverges. Since the integral diverges, then by the integral test, the series sum of 8 over 7k plus 12, k from 12 to infinite diverges. Example 2, use the integral test to determine whether the infinite series is convergent or divergent. Be sure to check the conditions of integral test are satisfied. So sum of 2k plus 9 divided by k squared plus 9k plus 12, k is from 1 to infinite. So f of x is continuous, decreasing, and positive for x greater than or equal to 1. Now determine if the improper integral to x plus 9 divided by x squared plus 9x plus 12 times dx, this is from 1 to infinite, is convergent or divergent. To calculate the antiderivative, integrate using substitution. So let u equal to what we have here in the denominator, x squared plus 9x plus 12. Then based on that, derivative of u is equal to 2 times x plus 9 times dx. So integral of 2x plus 9 divided by x squared plus 9x plus 12 dx is equal to integral du over u, so that is equal to natural log of absolute value of u plus c, which is constant, and that is equal to natural log of absolute value of, instead of u, now here we have x squared plus 9x plus 12, and then add constant. Next step, use the antiderivative to determine if the improper integral is convergent or divergent. So here we have integral to x plus 9 divided by x squared plus 9x plus 12 dx. This is from 1 to infinite. That is equal to limit of integral to x plus 9 divided by x squared plus 9x plus 12 dx. This integral is from 1 to b as b approaches infinite. So that is our limit. And this is equal to limit as b approaches to infinite. So limit of natural log of absolute value of x squared plus 9x plus 12. So here on this part we integrate, and that is equal to, so for this part, integrate is natural log of absolute value. And this is from 1 to b. So first using b instead of x here. So this is equal to limit of natural log of absolute value of b squared plus 9b plus 12 minus natural log of, now we use 1 instead of x, so natural log of 1 squared plus 9 times 1 plus 12. So this one says that b approaches infinite, Having infinite on this part, natural log of infinite is equal to infinite. It doesn't matter what we have here. Infinite minus any number, again, is equal to infinite. So here we have infinite. Since integral of 2x plus 9 divided by x squared plus 9x plus 12 times dx, this is from 1 to infinite. This one is equal to infinite. Because of that, the improper integral is divergent. What that means, the series sum of 2k plus 9 divided by k squared plus 9k plus 12, k from 1 to infinite, that is divergent. Does the series converge or diverge? So here we have sum of negative 1 over 25 to the nth power, n is from 1 to infinite. The geometric series is given by the general formula. Sum of a times r, power is n minus 1, and is from 1 to infinite. The p series is given by the general formula. Sum of 1 over n, power is p, and from 1 to infinite. Notice that the series sum of negative 1 over 25 to the nth power and from 1 to infinite is geometric series, since it can be written as sum of negative 1 times 1 over 25 to the nth power and from 1 to infinite. So this is exactly same as what was given here on this part, but I used negative 1 times instead of this negative sign. So we have negative times 1 over 25. So the geometric series are a series of the form sum of a times r, power n minus 1, and from 1 to infinite, and that is equal to a plus a times r plus a times r squared plus 3 dots plus a times r power n minus 1 plus 3 dots. And a and r are fixed real numbers, and a is not equal to 0. So the number r is called the ratio. So this one, r is called ratio if absolute value of r less than 1, geometric series converges. If absolute value of r greater than or equal to 1, the series diverges. So based on what was given, the series sum of negative 1 over 25 to the nth power and from 1 to infinite is geometric series, and r is equal to 1 over 25. The next step, absolute value of r is equal to absolute value of 1 over 25, and that is equal to 1 over 25, and this number is less than 1. Based on that, the series converges. So series sum of negative 1 over 25 to the nth power and from 1 to infinite converges. So series sum of negative 1 over 25 to the nth power and from 1 to infinite converges because it is geometric series whose ratio has absolute value less than 1. So what this means, absolute value of r is less than 1. Find out whether the series below converges or diverges. Sum of natural log of n plus 3 divided by n plus 3 and from 3 to infinite. So based on what is given on this part, our function f of x is equal to natural log of x plus 3 divided by x plus 3. Note that function f of x is continuous and always positive, as both the numerator and denominator are positive for all positive values of x. F of x is constantly decreasing. The term x plus 3, so we have in denominator x plus 3, that grows more rapidly than the term natural log x plus 3. This proves that the integral test applies to the series sum of natural log of n plus 3 divided by n plus 3 and from 3 to infinite. So we have all three the conditions of integral test. So it's positive, continuous, and here decreasing. Now determine whether the integral converges or diverges. Integral natural log x plus 3 divided by x plus 3 times dx. This is from 3 to infinite. That is equal to limit as b approaches infinite. Here we have integral of natural log of x plus 3 divided by x plus 3 times dx. This is from 3 to b. Now integrate. So integrate, and here we have limit as b approaches infinite. So integrate that part. Here we have natural log of x plus 3 squared divided by 2. This is from 3 to b. Now use b instead of x, and then subtract and use 3 instead of x. So we have limit natural log of b plus 3 squared divided by 2 minus natural log 3 plus 3 squared divided by 2. So that is equal to limit natural log b plus 3 squared divided by 2 minus, here we have 3 plus 3, that is 6. 6 squared is 36. So we have natural log 36 divided by 2. So here b approaches infinite. So we have natural log infinite, and that is equal to infinite. So subtracting this part from infinite, again we're going to have infinite. Since integral is equal to infinite, the integral is divergent. So that means the series sum of natural log of n plus 3 divided by n plus 3, and from 3 to infinite is divergent.